Welcome back to our series on identities and the like. This time we will be going a little bit further into it. Instead of just working with random identities and making random identities, we'll start adding very specific ones into the mix. Specifically, sum and difference formulas. So what we're going to do over the next few videos is first discover why we'd want these, and then how to make them, and then finally, how to use them. So the first video will probably be first motivating for the formulas and deriving them. Second video, making the difference formulas and using those to find exact values. And then finally, making cofunction identities and still more identities based on the sum and difference formulas. First things first though, why would we even want to bother? Well, let's say I wanted to find the cosine of 75 degrees and I wanted to find something like that exactly. Right, if it were 45 degrees, I could do that. If it were 30 degrees, I could do that. But if it's 75 degrees, do I have the ability to find that directly? Well, some of us might try and say, well, it's 30 degrees plus 45 degrees, so I've got cosine of 30 plus 45. So is that not the same as saying cosine of 30 plus cosine of 45? Is the cosine of 75 not the same as the other two? Is it not? Does the distributive property hold? Can I distribute the cosine across and have cosine of 30 plus cosine of 45, which I could then evaluate to be root 3 over 2 plus a half, which is 1.366. Well, there it is, right? I found it. So I guess I don't need more formulas. Or so I would say until I stop to consider, but cosine can't be greater than 1, right? Cosine can't be less than -1, can't be greater than 1. So whatever this is can't be right. Specifically, if I want to look up what cosine is, I would evaluate that through a calculator and find it's about a quarter. It's about 0.259. So this is entirely wrong. We cannot distribute cosine as if it were some scalar multiplier, which is sad to some. We'll go ahead and spell this out, because it's something that bothers me quite a bit. When does the distributive property actually hold? When can we just distribute something across, right? We know that multiplication is distributive, right? If I had a being multiplied onto some sum of two things, I can distribute that across and have ax plus ay. I understand that. But if this a were, say, cosine, then the distributive property apparently no longer seems to hold. But actually, this distributive property only holds for multiplication. That's probably why they call it the distributive property of multiplication. So addition's not distributive, right? A plus x plus y is not a plus x plus a plus y. Exponents is not distributive, right? X plus y quantity squared is not x squared plus y squared. Logarithms are not distributive. The logarithm of a plus b is not the same as the logarithm of a plus the logarithm of b. And if you want to see what that is exactly, you might want to consult your algebra side of pre-calculus. We actually go into what log a plus log b actually is, and it's not log of a plus b. So now we have one more thing to add onto the list of what is not distributive, and that is all of the trigonometric functions. Sine plus sine is not sine of a sum. The sum of two cosines is not the cosine of a single sum. Same for tangent. Cotangent, secant, cosecant. You just can't do it. In fact, in general, if you think you can distribute something across, you probably can't unless it is multiplication. So something to hold on in mind. Pretending that you can, especially when I've come so straightforward to say it's not, is going to make me very profoundly sad. So let's not. So what is the cosine of 30 plus 45? How would I go about actually showing what that is? How would I go about finding that exact value? Because I do believe I can. And to do it, I'm going to bring up my friend Desmos here. What I have right here for us is basically part of the unit circle. This line right here is of length 1, it's of length unity, so this point right here is on the overall unit circle. I just don't have it displayed right now because there's a lot of other things that are going to be displayed instead. So this angle right here that we're rotating by is going to be the sum of two angles, call it A plus B. And that's going to spit me up here at this point right here, which is going to be x comma y, which for being on the unit circle is cosine comma sine. So that's our point, cosine of A plus B comma sine of A plus B. Well, that's well and good, but I would like to find another way to get to this same point using just sine of A, or sine of B, or cosine of A, cosine of B, just all of those things. Cosine of single angle, if at all possible. And I do think it is possible, and I'll show you why. Right, this is my big triangle. This is for the overall rotation. Right, this base is cosine of A plus B, and this height is sine of A plus B. What I want to be able to do is find another way to get this same height and to get this same width. And how I'm going to try to do that is, instead of rotating all the way back down, I'm going to take this length and project it onto something halfway in between. Right, this value right here is projected straight down onto the x-axis, but what if instead I project it halfway? Specifically, what if instead of going all the way back down A plus B, I just go down B? So this angle right here is angle B, and this angle right here is angle A, and all that together got me the original rotation. And yeah, this is a right triangle now. This is still hypotenuse 1, it's still hypotenuse of unity. But what we've got is the base of this red triangle is cosine of B. This is really hard to do. And the height of this triangle is sine of B. You have to bear with me there. So we've got that, and that all together brings me to this point. The coordinates on this point is cosine B cosine A, comma, cosine B sine A. How do you get that, you ask? Well, recognizing that if I were to project this point back onto the x-axis, I've got now a right triangle. Angle A is the interior angle. Hypotenuse is cosine B. And so the base of this triangle is going to be r cosine theta, or in other words, cosine B cosine A. The height of this triangle is going to be r sine theta cosine B sine A. All right. Well, we're getting there. We don't quite have what we want, right? We want to end up at this point, but I claim to you that now we can get to this point with just a little bit more work. Specifically, looking at this remaining triangle that also exists. Right? This is a right triangle. The hypotenuse is sine of B. And so if I want to start here and go up to this spot, I need to find the height of this remaining right triangle. So let's see here. I believe the angle in question is going to be angle A, because I have A here, 90 here, so necessarily this has to be 90 degrees minus A, and so that plus this 90 degrees plus this angle altogether has to equal 180. So I've got 180 equaling 90 plus 90 minus A plus another angle. So that other angle has to be A. So that brings me to this point. I add to my previous height r cosine A, sine B cosine A. That brings me there. And finally, to end up at this original point, I have to subtract this base, which is going to be r sine A, or in other words, sine B sine A. And that puts me at the same spot. Beautiful. So now I have two ways of describing the same point. One is x comma y cosine of a plus b sine of a plus b. But now I see that that x-coordinate is the same as cosine b cosine a minus sine b sine a. And also the y-coordinates are the same. Sine of a plus b is equal to the sine of a cosine b plus cosine a sine of b. These are the way we go about finding the sine and cosine sum formulas. And also, I'm just going to throw this up here. I don't really want to get into the algebra right now. There is a way to take that, recognizing tangent is sine over cosine, and do a little bit of manipulation and end up with the tangent formula. I'll let you look at that here for a second, and I will pick you up in the next video where we will get into the difference formulas and actually looking at using these to find exact values for still more angles that we could not before. See you then.